Hello everyone, my name is Yuvraj, and I am excited to present our project titled Protein Classification Prediction Using Machine Learning. This project aims to leverage advanced machine learning techniques to classify proteins based on their structural attributes, which is a significant challenge in the field of bioinformatics. Today, I will walk you through the problem we are addressing, the methodologies we employed, and the impact of our finding. Let's take a look at the main points we'll cover in this presentation. Introduction to the problem. I'll start by explaining the context and significance of protein classification and why it's important in fields like bioinformatics and drug discovery. Opportunity evaluation. Then we'll discuss why this problem is an attractive opportunity for a machine learning solution, highlighting its potential impact on research and healthcare. Crisp DM business understanding. In this section, I'll outline our business objectives and success criteria, and explore the factors relevant to solving this problem effectively. Solution validation plan. Here we'll look at how we validate the solution, including model selection and iterative experimentation to ensure accuracy and reliability. ML system design. This part will cover how the machine learning system was designed, focusing on model selection, data preprocessing, and evaluation techniques. Potential risks in production. Next, I'll identify any potential risks that could arise when putting the model into production, such as data drift or concept drift, and how we plan to mitigate them. Summary of work done. Finally, we'll summarize the main achievements of the project, the impact of our work, and potential next steps. Let's begin by understanding the core problem we are tackling. Protein classification is the process of categorizing proteins based on their structural and functional properties. Proteins are complex macromolecules that play essential roles in virtually every biological process, including catalyzing metabolic reactions, replicating DNA, and responding to stimuli. However, the classification of proteins is not straightforward. The diversity of protein structures means that even proteins with similar amino acid sequences can exhibit different functions based on how they fold. This complexity makes accurate classification critical for advancing biological research and developing effective drugs. In essence, the ability to classify proteins accurately can provide insights into their function, interactions, and biological significance, which is vital for understanding various biological processes and diseases. Opportunity evaluation problem description. The challenge is to classify proteins based on their structural features, such as residue count, molecular weight, and crystallization method. Accurate classification is critical for understanding biological processes and diseases. Why machine learning? Impact on research. Protein classification is essential for bioinformatics, drug discovery, and personalized medicine. Scalability. Traditional methods are manual and slow. Machine learning can handle large data sets and detect complex patterns faster. Innovation potential. ML models, such as KNN and random forest, can revolutionize protein classification, improving accuracy and efficiency. Attractive opportunity. High impact. Enhances biological research, drug discovery, and healthcare by accurately classifying proteins, leading to better disease understanding and treatment development. Structured data sets. Availability of well-organized data makes it easier to apply machine learning models for efficient and automated classification. To structure our project effectively, we adopted the Crisp DM framework, which consists of several phases. Business understanding. We began by defining the problem and establishing success criteria. Our focus was on achieving high classification accuracy and ensuring that the model could be applied effectively in real-world scenarios, such as drug discovery. We identified key performance indicators including accuracy, precision, recall, and F1 score. Data understanding. We gathered relevant data sets that contained information about various proteins. This phase involved exploring the data to understand its structure and the features available for classification. We examined the distribution of classes, identified potential biases, and assessed the quality of the data. Data preparation. In this phase, we performed essential pre-processing steps, including normalization of data and handling missing values. Normalization ensures that features contribute equally to the distance calculations in algorithms like KNN. We also encoded categorical variables and split the dataset into training and testing sets to evaluate model performance. Modeling. we trained our machine learning models using the prepared data. This involved applying techniques like cross-validation to assess model performance and hyperparameter tuning to optimize the algorithms. We experimented with different configurations to find the best performing model. Evaluation. Finally, we evaluated the model's performance based on classification accuracy and its ability to handle large datasets. We used confusion matrices and ROC curves to visualize performance and ensure that our model is robust and reliable. This evaluation is critical to ensure that our model can be trusted in real-world applications. Business objectives. Enhance classification accuracy. The primary goal is to increase the accuracy of protein classification models. Achieving this will improve the reliability of predicting protein types, which directly impacts biological research, drug discovery, and disease understanding. Efficient protein function identification. The solution aims to streamline the process of identifying protein functions, traditionally involving labor-intensive and manual analysis. By automating this task with machine learning, researchers can make more informed decisions faster, leading to quicker breakthroughs in understanding protein behavior and their roles in diseases. Relevant factors. Protein, structural features. Important factors include characteristics such as residue count and molecular weight, which are crucial for effective classification. Choice of machine learning algorithms. The effectiveness of algorithms like k-nearest neighbors, KNN, and random forest plays a significant role in the success of the classification models. Quality and size of the dataset. The handling of missing or imbalanced data is essential, as it affects the model's performance. Data preprocessing steps. Steps like normalization and encoding of categorical features are vital for preparing the data for machine learning algorithms. Now let's discuss how we will validate the solution and assess its effectiveness. Solution concept. The solution involves using k-nearest neighbors, KNN, a simple but effective algorithm to classify proteins based on structural data. KNN was chosen because of its effectiveness in classification tasks and its ability to handle multi-class problems, which is common in protein classification. Experiment execution. To train and evaluate the model, we will split the data into training and test sets. The training set will be used to train the model, and the test set will be used to evaluate its performance. Perform hyperparameter tuning to optimize the performance of the KNN model, particularly the number of neighbors, K, and the distance metric. Use cross-validation to prevent overfitting, ensuring that the model generalizes well to unseen data. Validation strategy. We'll use several performance metrics to validate the model. Accuracy, the percentage of correctly classified proteins. F1 score, a harmonic mean of precision and recall, providing a more balanced evaluation when dealing with imbalanced datasets. Confusion matrix, to visualize the classification performance across different classes. Slide 13. Given the challenges we face, how can we leverage machine learning to improve protein classification? Machine learning automates the classification process, enhancing both accuracy and scalability. For our project, we focused on algorithms such as k-nearest neighbors, KNN, and random forest. These algorithms are particularly effective for classification tasks due to their ability to detect complex patterns in data. Model selection. We chose k-nearest neighbors, KNN, due to its simplicity and effectiveness in classifying proteins. It works well for high-dimensional data and can easily be scaled for larger datasets. Data preprocessing, handling missing data. Missing values are imputed using a technique like simple imputer, ensuring that the dataset is complete before training the model. Label encoding. The target variable, which is the protein type, is encoded into numerical values using label encoder. Feature scaling. We scale the features using standard scaler to ensure that no particular feature dominates the model training due to its larger scale. Model evaluation. We will perform cross-validation to evaluate how well the model generalizes to unseen data. We will use a confusion matrix to identify which protein types the model is struggling to classify. F1 score and with the ROC curve will be the primary metrics to evaluate the model's effectiveness in real-world applications. When deploying a model into production, it's important to identify potential risks and challenges. Data drift. Over time, biological data might change, which could affect the accuracy of the model. For example, newer protein structures may not fit the patterns the model learned from the older dataset. Concept drift. This refers to the shift in the relationship between input features, protein structures, and target variables, protein types, over time. As research advances, the understanding of protein functions may evolve, affecting model predictions. Mitigation strategies. Regular retraining. To combat data drift, we will retrain the model regularly using new data to keep it up to date. Continuous monitoring. We will continuously monitor model performance in production to quickly detect any degradation in accuracy. Model versioning. By keeping track of different model versions, we can easily revert to an earlier, more reliable version if a new model performs poorly.
In conclusion, our project demonstrates the power of machine learning in addressing the challenges of protein classification. By enhancing classification accuracy and streamlining the identification of protein functions, we contribute to advancing biological research and improving healthcare outcomes. The integration of machine learning into bioinformatics not only improves efficiency, but also opens new avenues for research and discovery. As we continue to refine our models and explore new algorithms, we anticipate even greater advancements in this field.